The owner of a cafe wants to estimate the amount of coffee consumed in one day by coffee drinkers. A study which collected reports from a random sample of 55 coffee drinkers found that the average number of ounces consumed in one day by the coffee drinkers was 30.1 ounces. The standard deviation for these values was 7.9 ounces. Use the data to form a 90% confidence interval to estimate the true mean amount of coffee consumed each day by coffee drinkers. The owner of the cafe believes that coffee drinkers consume at least 32 ounces of coffee per day on average. Does the confidence interval you created support her belief? Okay, so let's start with the first thing in the problem, which is the idea of what are they asking us to do ultimately, right? And when I find this phrase here, use the data to form a 90% confidence interval to estimate the true mean, that sort of summarizes the whole idea of the problem, right? We need to use the data to construct a confidence interval for the purpose of estimating the population mean. Okay, so we'll go to our formula card, we look up our formulas, and we'd begin with that. But the one thing I want to suggest is that in the beginning, it's best to work with a set of steps that are pretty easy individually, and that way eventually you can move on and become faster at working it out. But in the initial phase, you'll develop good habits. So here's what I'm going to do. I'm going to say you should copy down the data from the problem first. And what that means is just fill in this list. You're going to need a sample size in these problems. You're going to need a sample mean. You're going to need some kind of a standard deviation. Usually it's a sample standard deviation. And then you will need a confidence level and perhaps an alpha as well. Okay. Of course, the confidence level and alpha are joined or linked together. You can get one from the other. So that's why I say you may not need the alpha because, of course, you may know it from knowing the confidence level. But we'll write it down just to have good habits. So let's start with the sample size in the problem. How many coffee drinkers were sampled? It looks like they used a sample of 55. So I'm going to say n is 55. What about the sample mean? It looks like they say that the sample mean here was 30.1 ounces of coffee for that group. The standard deviation for the data was 7.9 ounces. And then the confidence level is 90%. And from that confidence level of 90%, you can tell that alpha would be 10% or 0.10 as a decimal. All right, so we have our data. The next step after getting the data is to come up with a critical value. So the critical value, and here we're going to say that we need a critical z value. The reason why we're going to say we need a critical z alpha divided by 2 value here is because our sample size is over 30. That's going to be our criteria for when we use a z critical value. At this point in the course, you may not realize there's another type of critical value called the t critical value that we might use. And if you're not aware of that, it's okay, don't worry about it. Later on, it'll make sense that we're saying when the sample size is large, we will use a z critical value. When the sample size is not large, or in other words, when it's 30 or less, we'll use a t critical value. So over 30, use z alpha divided by 2 though. Okay, so what does that mean for us essentially? Well, it means that we have to look up our confidence level on our t-chart in order to find the corresponding critical value. Now in my class, you would just go and look up 90% on your t-chart. If you don't have that table though, you'll have to look up alpha divided by 2. So just to fill in the notation here, if this says alpha divided by 2 and your alpha is 10%, then alpha divided by 2 is 0.05. So we're going to look at the column on the t-chart that has 0.05 at the top of it. At the very bottom of that column, we will find the corresponding z-score we need. Okay, so here we are on our t-table, and we're looking at 0.05 here. We're looking at this position because this position is where we will find our corresponding z critical value at the very bottom of this table. So let's go all the way down to the bottom. And sure enough, you see for a 90% confidence level, it's 1.645. That is your critical value. So 1.645. Okay, so our z 0.05 critical value here is 1.645. Remember what that is? That is the z-score that leaves an area of 5% in the upper tail, right, of the distribution. So there's only 5% of the values under the z-curve that are above 1.645. Okay. That's your critical value though. Let's move on to the next step. The next step is the margin of error. So the margin of error, sometimes a problem will ask you just to calculate that, but it's also the third step of constructing the confidence interval. So if you're asked to construct the margin of error, you can just work from the same steps we did to create the confidence interval in this problem. Okay, so let's begin with the formula. It's E is equal to z alpha divided by 2 times the standard deviation divided by the square root of n. If you fill in those items, you will have the margin of error in this problem. Okay, so z alpha divided by 2, well, we had that from step 2 of our process, so it'll be 1.645 times the standard deviation. That number is 7.9 in this problem, so 7.9. Notice how we have a sample standard deviation. We're using it as a substitute for the population standard deviation. We'll assume that that's okay. Our n is 55, so we'll put a 55 here at the bottom. And then we have to work this out. Okay, so we'll need a calculator for that. So we'll have 1.645 times 7.9 divided by the square root of 55. Notice how we don't use any special parentheses or anything. We just kind of put it in as we see it. Press enter and we get 1.752 approximately. We'll probably round this answer to 2 decimal places after the decimal point, so it's okay if your margin of error has at least, say, 3 decimal places, okay? You might want to carry more if you're concerned. In fact, what I'll do in my calculator, just to show you what's the best practice, I'll store it as a variable x. So now it's stored in my calculator and I have it there, okay? In fact, I could even store that in my calculator as e. I'm going to do that just because it'll be more visually appealing. So I'm going to say store alpha e here, and this way it actually uses the variable letter e. Okay, the final step of the process is actually the easiest step of the process. What we're going to do for the very last step is we're going to fill in this little tiny formula. X bar minus e, comma, x bar plus e. This will complete our interval. So we saw that x bar was 30.1, and we saw that e is approximately 1.752. And then we'll have 30.1 plus 1.752. By adding and subtracting the margin of error from the x bar, it will basically give us 2 numbers on the number line where we think the population mean lies between. Okay, so we'll just quickly do that. 30.1 minus that error, which we saved as e. And so for the first part of it, we get 28.35 approximately. And then for the second part, just recall that same calculation I did, and I will just hit plus between it, now adding the error to the sample mean, and we get 31.85 this time. Again, that's to 2 decimal places. All right, so there's my interval, and what I want to do now is sort of interpret it. There's sort of a generic statement that you always say when you have these confidence intervals, and that generic statement goes like this. We are blank % confident the true blank is between blank and blank. All right, so what you fill in these spaces is just basically the details of the problem. For example, in this problem, we're 90% confident that the true, this problem is about the mean. It's specifically about the mean quantity of coffee drunk in ounces, but we'll just leave it as mean because somebody can read the problem to see what mean we're referring to. And then it's what? About 28.35 ounces to 31.85 ounces. And again, you could add in the unit of ounces if you want. But again, in the context of the problem, we know that these are ounces. Now, that's our interval. And a lot of students in statistics think it's okay just to get the interval, the numerical answer, because they're so used to taking classes where in mathematics, the numbers matter most, and that's all that we care about. That's not really the case here, right? We need to interpret the numbers. They need to speak to us and tell us something of usefulness. If they don't, then they're of no value to us, right? So what we want to do here is to say, what does this mean? Well, the first thing we want to say that it means is that we're highly confident, right? 90% confidence is pretty confident, right? Maybe not as high as it could be. It could be 99%, for example. But either way, we're highly confident that the true population mean is somewhere between these two numbers, right? So it could be as low as maybe 28.35 and as high as 31.85. But we do believe with 90% confidence that the true population mean is between these two values. Now, if you remember, the problem said that the owner of the cafe believed that coffee drinkers consume at least 32 ounces. So let's highlight that sentence there. It said that the owner believed that they consume at least 32 ounces of coffee per day. So does that sound credible here? Does it seem like that is true based on the interval? So the question they're asking is, does the confidence interval you created support her statement? Well, all right, well, if we look at the numbers here provided by the interval, it doesn't appear that this interval confirms her belief, right? The reason why I say that is because the interval doesn't include 32 ounces, and she's saying at least 32 ounces. So she's saying coffee drinkers drink 32 ounces or more. Now, granted, if you round it off to a whole number of ounces, 32 is actually part of the interval, but I would say that, in this case, it falls a little short of that, right? And again, we believe that the population mean is somewhere between these two values. And granted, maybe it could be 31.85, but it's not 32. It seems to be something that's most likely less than 32 ounces. She's saying it's 32 ounces or more. I don't think the interval really provides strong evidence for that, right? In fact, it doesn't seem to provide evidence for that at all. The mean here seems to be a number that's technically less than 32 ounces, right? The values in the interval are all lower than 32, so it doesn't seem that she's actually correct. The last thing I want to say about the interpretation here is that if we constructed interval after interval after interval after interval, right, using a sample of 55 coffee drinkers again and asked them the same question, how much coffee do you drink per day, or measured that some way, maybe by tracking them or something. Either way, the point is we collected, data from the same population and we did it over and over again with different samples, right? And each time we created a 90% confidence interval. We're saying that basically 90% of those intervals we create should contain the population mean. But there would be about 10% or 1 in 10 intervals that don't contain it. So it's possible that this could be one of those 1 in 10 intervals that don't do their job. But, again, we have a 90% sort of chance of a randomly chosen interval actually containing the population mean, right? But again, we have this idea that, 90% of the time when we grab a sample from the population, the constructed interval will contain the population mean, right? Whether this particular interval does or doesn't, we don't know, right? So either the mean is in there or it isn't. But, the point was before we initiated the process, there was a sort of a 90% chance that the sample we would choose from the population would end up producing an interval that would capture the population mean. So our instinct says that most likely this interval does contain the population mean.